we can see 13 billion years in the past. Imagine peering backwards in time, and not just decades, but billions of years to the dawn of the universe as we know it. With the James Webb Space Telescope, we can do just that. By collecting faint light from distant galaxies, we see them as they were in their youth, mere cosmic infants. It's like looking back through a time tunnel, witnessing the universe unfold after the Big Bang. Light travels at a finite speed, so the farther we see, the farther back in time we go. These galaxies hold the secrets of the universe's first dance, the formation of stars and of galaxies from swirling clouds of gas. We are essentially archaeologists of the cosmos, piecing together the universe's history with every observation. These glimpses into the deep past challenge our understanding of physics and force us to rewrite the narrative of our own cosmic origins. It's a humbling and awe-inspiring realization. We are not just stargazers. We are time travelers, looking back at the dawn of existence. On December the 25th, NASA launched the James Webb Space Telescope, the world's largest observatory to date. Now, arguably, astronomy's greatest success story. The JWST took 25 years to make and is 100 to 1,000 times more powerful than any previous telescope. Despite the tennis court-sized craft's 344 single points of failure, a fault at any one of which could cause total failure, the deployment of the telescope was a glorious success. It has now reached its home at L2, a gravitationally stable spot known as the Lagrange point, over 1 million miles away from Earth. Inspired by an iconic image of distant galaxies shimmering against an endless sea of black taken from JWST's predecessor, the Hubble Space Telescope, the team at NASA embarked on a mission to try and study even further back into the universe's origins. The project has spearheaded numerous technological advancements and revealed to us what were once merely secrets of the cosmos. In this video, we will be diving into JWST's recent discovery, the oldest structure ever captured. On March of this year, the James Webb Telescope captured the impossible, the oldest and largest merger of young galaxies we have ever seen in the early universe. Its name? GZ9P3. Oh, science, always keeping things catchy and memorable. So, how old is old GZ9P3? 13.8 billion years old. And how old do scientists reckon the universe is? 13.8 billion 400 million years old. Half a billion years after the Big Bang is still a decent chunk of time. But let's not downplay this impressive achievement. Up until a few years ago, GZ9P3 was a single point of blobby reddish light found by James Webb's older brother, the Hubble telescope. But with the help of James Webb's near-infrared spectrograph, aka NIRSPEC, this little slice of universe pie has gone from a mysterious morsel to a more mature and meatier marvel than we could ever have predicted. Infrared. So, how does the near-infrared spectrographic technology on the JWST work to capture the ghosts of the cosmos? First things first, let's talk infrared light. Ever since the Big Bang, the universe has been eating all the cake, as in, it has been expanding. A bit like a fruitcake, the distance between the raisins, aka the galaxies, has been increasing. This means that older galaxies are moving away from us at an exponential pace. As they move away, a phenomenon called redshift, pushes the wavelengths of light out of the visible spectrum and into the infrared spectrum. The James Webb Space Telescope is an infrared telescope, which essentially means that it sees with light which is invisible to human eyes, allowing it to see through otherwise opaque dust in the universe to view hidden stars and planets. James Webb's predecessor, the Hubble Space Telescope, had limited infrared imaging capabilities, only detecting a small portion of these wavelengths. This means that in the past, our ability to see the oldest parts of the universe in high detail were limited, as these galaxies and planetary bodies are redshifted far beyond the visible light spectrum. The JWST, however, is equipped to see galaxies deep in the infrared, allowing us to capture images of galaxies over 13 billion years old, like the galactic wonder of GZ9P3. Though it's no catchy moniker, the ancient structure was dubbed GZ9P3 by the GLASS Collaboration, an international research team from the University of California. This nomenclature reflects the galaxy's redshift value of Z equals 9.3, with G and Z9P3 serving as identifiers derived from the concept of redshift. Preliminary Patriarch, however, might have been a better name. Inaugural Ian or Early Eve, something poetic like that. Okay, enough. Spectrography. So the infrared technology contained within the JWST was able to help capture the light coming from GZ9P3. But what is the spectrograph aspect of NIRSPEC, and why is it the sharpest tool in the space shed? Otherwise known as spectrometer, a spectrograph is used to disperse light into a spectrum. When we peek at an object's spectrum, like a star or galaxy, it spills the cosmic tea on its life story, temperature, mass, even its choice of chemical cocktails. How hot is it? What does it look like? What drugs does it have on its person? It's like reading its interstellar horoscope, only unlike astrology, all its findings can be explained by the scientific method and not mere delusion and the allure of symbolic systems that distract from a world governed by entropy and capitalism. Anyhow, let's talk mirrors. Mirror technology. So the James Webb is up there hanging out at the Lagrange point, studying these faint objects like they are secrets at a gossip party. Galaxies so shy they make wallflowers look like socialites. But to get the real scoop, it's gonna need something more than its infrared eyes. It's gonna need some fancy mirrors. The telescope contains a whopping 18 mirrors that fan out to form a single mirror over 6 meters in size. According to JWST's optical telescope element manager Lee Feinberg, each of these 18 hexagonal mirror pieces of the upper section had to align within 1/5000th the width of a human hair to extract ample light for spectral analysis and hence discover preliminary Patricia, aka GZ9P3. The Webb's colossal mirror dedicates hundreds of hours to each target, enabling the examination of thousands of galaxies over its 5-year tenure. The NIRSPEC boasts a pioneering feature: the ability to concurrently observe 100 entities. How nosy! This groundbreaking multi-object functionality marks a first for space-based spectrographs. Achieving this first necessitates the development of a novel micro-shutter system by Goddard scientists and engineers, which governs the entering of light into the NIRSPEC, JWST's micro-shutter array. The NIRSPEC employs a distinctive technology known as micro-shutter array to facilitate the acquisition of 100 simultaneous spectra. These micro-shutter cells feature lids that can open and close through the application of a magnetic field, like the fanciest of eyes you ever did saw. With individual control over each cell, they can be manipulated to either reveal or obstruct specific portions of the celestial expanse, a cosmic peekaboo, if you will. Given the considerable distance and faintness of the targeted objects, it becomes imperative to mitigate the interference caused by nearby bright sources of light. The operation of microshutters mirrors the human act of squinting to hone in on a focal point by selectively blocking out extraneous light. Good luck trying to squint at the sky to find GZ9P3 because you're never gonna see it. Only the James Webb Telescope can. Adjusting ideas about the early universe. What has discovering GZ9P3 led to in the field of astronomy? Science is constantly changing. After all, the only thing that remains constant is change itself. When astronomers and space scientists observed GZ9P3 and saw how large it was, how quickly the galaxies had developed considering its relative youth, and noted how chemically mature the galactic merger is, they were surprised, to say the least. These observations offer proof of a swift and effective accumulation of stars and metals shortly after the Big Bang, attributed to continuous galaxy mergers. They showcase the existence of massive galaxies containing billions of stars much earlier than previously anticipated. So, does that mean that the space folks have got it all wrong? Not necessarily, but the current model of galaxy formation has to be thrown in the air and tossed about a little in light of GZ9P3's findings, not unlike a comet speeding past your retinas on a dark night. As we near the 2-year milestone for scientific observations conducted by the JWST, these fresh findings arrive at an opportune moment. With an expanding pool of observed galaxies such as GZ9P3, astronomers investigating the early universe are shifting from mere discovery to a phase where sufficiently large data sets allow for the development and enhancement of new models. Exciting stuff! So, what lies ahead for the James Webb Space Telescope? The James Webb Space Telescope was designed to last 5.5 years with a goal of 10 years, fuel permitting. So it's got plenty of time to shock the world and reveal to us even more wonders of the cosmos. Alongside capturing incredible glimpses into the early universe, the telescope has made other exciting discoveries like Stephan's Quintet, a group of 5 colliding galaxies as seen here. The image of this galaxy cluster also reveals black hole outflows in a manner never seen before in this region of our universe. The telescope has also developed astronomy's understanding of various nebulas and exoplanets. For instance, the Carina Nebula, looking like some sort of celestial cliff face, was captured in the JWST's salad days. The future of astronomical exploration holds immense promise. Not only is the JWST poised to unveil phenomena like colliding galaxies, dying planets, and extreme worlds, it may even provide insights into extraterrestrial civilizations. The JWST's focus on detecting infrared light, vital for uncovering the mysteries of exoplanets, is central to this endeavor. If we already have evidence of water on exoplanets, the potential for life to exist beyond our own planet becomes a tantalizing possibility. Who would have thought that the space race would get this far? And who knows where we will be after the pale blue dot takes another trip around the sun? The team at Astronomy Revelations, however, will be right here. If you enjoy our silly intergalactic wordplay and are a fellow fan of all things space, click the subscribe button. Till next time, space lovers.